Alright, in this section we're going to take a look at specifically how mechanical energy is conserved. And it should come as no surprise to you by this point in time that I'm going to tell you that overall energy is conserved. And that's actually shown in this equation right here, because what we're looking at here is we're saying that if the change in kinetic energy and the change in potential energy don't balance each other out, then that must mean that something else did work that will accommodate or account for that missing or added energy. And that is a work of a non-conservative force, which either acts initially or over time or from an outside source into a system. But energy is conserved. We can find that energy either within the system itself or within the system and its surroundings, if we're going to locate where energy came from or where energy went to. But we're going to be looking more specifically at a situation where mechanical energy itself is conserved. So that means that we're going to be looking at a situation where only conservative forces are acting in a system. Another way of saying that is that if only conservative systems are acting in a system, then that means that there will be no work done by non-conservative forces. If there's no work done by non-conservative forces, something really awesome happens to our equation. The non-conservative forces is going to equal 0. So that means the change in kinetic energy and the change in potential energy, when summed up together, will be 0, which means that there's not going to be any change overall in the total energy of the system. And that will always be true as long as no non-conservative forces are working in a system. So I'm going to do a little bit of equation manipulation here so we can get into a concept or a mathematical way of looking at a concept and considering how or the power of this particular phenomena. The change in kinetic energy I show here by breaking it down into Ke2 minus Ke1, and the change in potential energy I break it down into Pe2 minus Pe1. And according to this equation, if no non-conservative forces work on the system, that sum will equal 0. I furthermore break it down so that I have no negative. So that means that I arrange Ke2 positive on this side, Pe2 positive on this side, and then I bring the Ke1 and the Pe1, which are negative on this side, over to this side so that they're positive. So what I'm saying is that the kinetic energy at the second position that we analyze, along with the potential energy at that same position, see they're both at the same position because they're both designated as position number 2, are going to be equal to the kinetic energy of the object in its first position and the potential energy of the object in its first position. Now here's where we can get into an important definition. But what so what I'm going to give you finally is a definition, an actual definition for mechanical energy. The total mechanical energy is the sum of the kinetic and potential energies at any one point in a system. So here it is. We say that mechanical energy is just the total of any potential energy that an object has and any kinetic energy that an object has at any one instant. So that means that if you're considering yourself a system, you would have to consider your potential energy and your kinetic energy. So it would be how much potential energy you have due to a force, and that has to be a conservative force since it's potential energy, and how much energy you have due to your motion, and that would give you your total mechanical energy. Mechanical energy is most often designated as E, and sometimes you'll see me call mechanical energy ME, and that's just habits die hard from general physics. So the energy is equal to the kinetic energy and the potential energy of an object, and that energy can be analyzed at any point in time for a system. And if no non-conservative forces are acting, then that energy is conserved. So what we're saying in this equation is that if energy equals Ke plus Pe, then the energy of the system at the second point that we analyze will equal the kinetic energy at that second point plus the potential energy at that second point. And if no conservative forces are working, that amount will be equal to the kinetic energy at the first point and the potential energy at the first point added together. So what we're saying is that the mechanical energy of a system at one instant will always equal the mechanical energy at any other instant that we analyze. This value is constant. When you add all the pieces up, you'll get the same number every single time. And this is an incredibly powerful tool to have. Remember that this is true when no non-conservative forces act on a system. Conservative forces have potential energy. Non-conservative forces must not be acting. The total mechanical energy of a system is conserved. Mechanical energy becomes a conserved quantity. That number will be the same number every time you calculate it, no matter what has occurred over time. Kinetic energy plus potential energy 1 will equal kinetic energy plus potential energy at the second point. We know what the kinetic energy and potential energy equations are, so if we're considering a system acting by gravity, so another way of saying that is another rearrangement. The change in potential energy will be equal and opposite to the change in kinetic energy. So in a conserved system, if kinetic energy increases, that means potential energy had to decrease by that exact same amount. If potential energy increases, kinetic energy has to decrease by that exact same amount. So there's an inverse relationship between the kinetic and potential energy at any one point in a system where mechanical energy is conserved. So this is important. If only conservative forces are acting, the total mechanical energy of a system neither increases or decreases in any process. I'm going to say it over and over and over again because by the power of this concept, you will be able to work your way through so many situations so much easier than other physics concept problem solving. So that means that when no non-conservative forces are working, the total mechanical energy stays constant and it's conserved. This is called the principle of conservation of mechanical energy for conservative forces. And remember, conservation of mechanical energy depends on there being only conservative forces acting. If non-conservative forces are acting, we will look at a system that will allow us to solve for those problems, but you cannot use conservation of mechanical energy when non-conservative forces are present. So let's go ahead and let's take a look at problem solving for conservation of mechanical energy. And we're going to start with a super simple system. And our super simple system is an object in free fall. And the reason that we can consider this a simple system to analyze the conservation of mechanical energy is that if we neglect air resistance, then there's only one force acting, and that force is gravity. And that's why we call it free fall. And gravity, we know, is a conservative force. So that means that any object experiencing free fall where we can neglect air resistance is going to be a demonstration of conservation of mechanical energy. The total mechanical energy at any point along this line is going to be the same number. So that means that the total mechanical energy here, if we say that that total amount equals 10 up here, it'll equal 10 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 here, so on and so forth. It'll even equal 10 at the bottom the moment before it hits the ground. Now, remember we talk about our problem boundaries, and the moment that it hits the ground, the moment that it comes into contact with the surface, it will have another force that's not gravity on it, so that means that it's no longer in free fall. We consider the problem boundary here to be the situation where it's experiencing free fall, and the moment it stops experiencing free fall, we stop considering the situation to fall under the conservation of mechanical energy. So how is it possible? How is the total energy the same the whole time? Well, if we think about it, at the top, right, if we consider its top height, it's motionless, right? Its velocity equals 0. All of its energy at that point in time is potential energy due to gravity. So that means that the total energy here, which is potential energy plus kinetic energy, would be equal to, well, velocity is 0, so kinetic energy is 0. So at the top, all of the mechanical energy is potential energy. As soon as this gentleman here, in disguise, drops the rock, it will begin to experience free fall motion, and it will accelerate due to gravity. If it's accelerating due to gravity, then as it falls down, its velocity increases until at the halfway point, half of its energy is kinetic energy, and half of its energy is potential energy at the halfway point. And that makes sense because up here, potential energy is mgh. Right here, total energy is kinetic plus potential. Potential is mgh, but this time h is 1/2 the original height, so this one is mgh over 2. So that means that now at this point, the energy due to potential energy is only half the amount that it was. So that means the other half of the energy must be kinetic energy. And then at the bottom, the height now equals 0, so the energy will equal PE plus KE. And since the height is 0, there will be no potential energy, which means 100% of the mechanical energy at the bottom, the moment before it hits the floor, is all kinetic energy. So we could use this concept if we knew the initial height and we knew that we were neglecting air resistance. We could use this situation to calculate the total mechanical energy in the system, which is conserved, and we could use that to figure out the velocity at any point in time of the falling rock, which is a pretty neat thing if you ask me. So let's go ahead and take a look at that. Here we have just that. We have a situation where we're going to be considering a falling rock. And what I want to do here is I'm going to say if the original height of the rock is 3 meters, calculate the rock's speed when it has fallen to 1 meter above the ground. And we can also calculate its speed right before it hits the ground. But let's first follow the instructions, and we want to consider what's the velocity at this point. And here I have a value shown as 6.3 meters per second. I'm going to prove to you that that value is in fact correct. So we know that the velocity at the top is equal to 0. We know that this is a conservation of mechanical energy problem. Therefore, the energy at any one point along the way is going to be the energy at any other point along the way. So we're going to call this point number 1, we'll call this point number 2, and we'll call this point number 3. So, just like before, an object experiencing free fall, we're neglecting air resistance, so there's no non-conservative forces working. That's why this equation is true. As soon as the rock is released, it begins experiencing free fall, and we can apply the conservation of mechanical energy the entire time it's in free fall. At the top, its velocity is 0, so all of its energy equals Ke plus Pe. If its velocity is 0, its kinetic energy is 0, because remember, kinetic energy equals 1/2 mv squared, and if velocity is 0, so is kinetic energy. And potential energy here is going to be mgy, so our total mechanical energy will be given at this point by the potential energy. And if the rock has a mass of, we don't know. So that means that the total energy here is just going to be mg, and we're going to call this y1. That's the total energy. That total energy is the same amount that it will be down here. So E1 here is going to be equal to E2 here. What is E2? Here, we don't know what the velocity is. I mean, we do, but we're going to pretend that we don't know what the velocity is. But we know that E2 should be equal to 1/2 mv2 squared plus mg y2. And we're looking at compared to this reference point of y0 at the ground. So in that case, since E1 and E2 are equal to each other, I can set mgy1 equal to 1/2 mv2 squared plus mgy2. So I'm going to do just that. I'm going to say mgy2 or y1 equals 1/2 mv2 squared plus mgy2. Now once I do that, the mass of the rock suddenly no longer matters because it happens to appear in every single piece of the equation. So I can eliminate the mass, and then I get that gy1 is equal to 1/2 v2 squared minus gy2. Now I can combine variables here, plus, and then I get gy1 minus gy2 equals 1/2 v2 squared. And then I can say that v2 squared is going to be equal to 2 times gy1 minus gy2. Square root of both sides, and I get that the velocity is going to be equal to the square root of 2g y1 minus y2. Just cleaned it up a little bit. So that means that the velocity is going to be equal to the square root of 19.6 times 3 minus 1 or solving that out, I got 6.26 or 6.3 meters per second. So I was in fact able to confirm using conservation of mechanical energy that that should be the velocity when it's 1 meter above the ground. I can likewise use this concept to show that the velocity is 7.7 meters per second at the bottom. And I could do that by either setting E3 here equal to E1 or setting E3 equal to E2. They're both going to work, and I want to show you that that's true, and that if you know the energy at one point, you can use that equation, or you can use that feature of that equation to solve for any other point. So first I'm going to do it by setting E3 equal to E1. Well, E3 here is going to be equal to mgy3 plus 1/2 mv3 squared. Y3 is 0, so that means that the energy at point 3 is going to be 1/2 mv3 squared. So I could set 1/2 mv3 squared equal to E1, which I decided was mgy1. Conveniently eliminate that pesky mass, and now I get 1/2 v3 squared equals gy1, or v3 equals the square root of 2gy1. So v3 equals the square root of 19.6 times 3. Or 7.7 meters per second. So I used conservation of mechanical energy to show that from the beginning to the end of the system, the energy was conserved, and that allowed me to predict or confirm the velocity all along the way. Now, since the energy is conserved and E1 equals E2, I could have also done that by setting E2 and E3 equal to each other. E2 was 1/2 mv2 squared plus mgy2. So I set that equal to E3, which was 1/2 mv3 squared. 1/2 mv3 squared equals 1/2 mv2 squared plus mgy2. Get rid of my masses. And I get that 1/2 mv3 squared is going to be equal to 1/2 mv2 squared plus mgy2. So that means that v3 is going to equal the square root of mv2 squared plus 2mgy2. Sorry, my m's are gone. I didn't mean to write them again. So now I can plug in 6.3 squared plus 19.6 times 1 meter. Square root of that, and I get the same answer, 7.7 meters per second. Now, comparing these two, you can see that the calculations are a little bit more straightforward using this, but it's going to work either way, and so that's a really convenient thing for you to know. The velocity in a conserved energy quantity or a conserved energy problem that involves gravity is independent of mass. It's only dependent on the amount of potential energy that an object has. And since potential energy and kinetic energy are directly related to the amount of mass, in a problem where only gravity is working as your non-conservative or as your conservative potential energy force, and kinetic energy is your other problem, then that means that you can go ahead and always find values independent of mass. Another thing to take a look at is that this equation, right, 1/2 mv squared plus mgy for that one point is equal to 1/2 mv squared plus mgy at another point. This is always going to be the equation that you can apply to a situation where an object is acting by gravity and you can ignore friction. Because if an object is acting by gravity, some form of friction is the only possible non-conservative force that you have. So if you can ignore or neglect friction, the conservation of mechanical energy given by this equation is always going to work. Let's go ahead and let's take a look at another type of problem that we can solve using this concept that would be an incredible pain in the butt to do using kinematics. We're going to take a look at example 6.9, a roller coaster speed using energy. So in this case, we have a roller coaster of height y at this top point. So we'll call this point y. We'll call this point y1, or we'll just set this point over here to y equals 0. And this will be y1, this will be y2, and this will be y3. In this problem, we're going to take a look at a situation. We're going to say the height of the hill here, y1 equals 40 meters. And the roller coaster car starts from rest at the top. So the velocity at y1, which we'd call v1, is 0 meters per second. So we're saying that the velocity here equals 0. If this is the situation and it's starting from rest, we can calculate the speed of the roller coaster down here at y2. So that means we're going to be finding v2 at y2, and we're also going to be able to figure out at what height it will have half of the speed. We won't be able to do that without finding out what that speed is, but we'll also be able to find out y3, which is when v2 over 2, or half of that velocity. So we could do this problem because we know that the energy is conserved. So the energy at any one point, the mechanical energy at any one point, is going to be equal to the mechanical energy at any other point along the way. So we're going to call this first position Y1. We're going to call that E1. At E1, the top of the roller coaster, velocity equals 0. So this situation where E1 equals PE1 plus KE1, since the velocity is 0, the kinetic energy is 0. So that means that E1 is going to be equal to mg Y1. At point E2, energy equals the potential energy at point 2 plus the kinetic energy at point 2. And that means that since Y2 here we set as our reference point, we set it at 0, and that means that the potential energy there is going to be 0, so E2 is going to be equal to 1/2 mv2 squared. And since the mechanical energy is conserved, in other words, we can ignore the friction that occurred as the roller coaster traveled down that path, then we can set E1 and E2 equal to each other, and we can say that mg Y1 equals 1/2 mv2 squared. Eliminate the mass, and we get that V2 is going to be equal to the square root of 2g Y1. So that means that V2 equals the square root of 19.6 times 40. So V2 actually equals 28 meters per second. So now that we've found that value using the conservation of energy, we know that if we continue to neglect friction, the roller coaster will have the exact same energy at the point E3. And E3 is going to be made of the potential energy at point 3 plus the kinetic energy at point 3. And the only thing we know about point E3, we don't know what Y3 equals. We just are unaware of it. But we do know that at point E3, the point that we're interested in, the velocity that we found at Y2 is cut in half. So that means that the velocity is going to be 14 meters per second. So E3 is going to be equal to mg Y3 plus 1/2 mv3 squared. And that's equal to the energy at point 1 and point 2. So we could choose whichever one we wanted and we would be able to solve. Just for the heck of it, I'm going to use E1. So I'm going to say that mg Y1 is equal to mg Y3 plus 1/2 mv3 squared. I'm going to eliminate my masses. And that means that gy1 equals gy3 plus 1/2 v3 squared. Solving for y, I get that gy3 equals gy1 minus 1/2 v3 squared, and I'm going to divide by g. So y3 equals this value. So I'm going to say 9.8 times 40 minus 1/2 times 14 squared divided by 9.8 equals y3, and my y3 value equals minus 2 times 14 squared. Oops. 9.8 times 40 minus 14 squared times 0.5 divided by 9.8, and I get that y3 equals 30 meters. And you could have just as easily solved it using 1/2 mv squared for position number 2. So let's look at a conceptual example. An example where we don't necessarily have to calculate anything, but we have to take a look at how the values of potential and kinetic energy change and what that means. Here you see we have on the water slide Benny Paul and Benny Kathleen. And Benny Paul and Benny Kathleen start at the exact same height. So the height that both of these guys start at is the same. And they're the same length from start to stop. And Benny Paul and Benny Kathleen start from rest at the same time on the 2 different slides. So they both started at time equals 0 up here. And so we want to know, first, which rider, Benny Paul or Benny Kathleen, travels faster at the bottom, and which rider makes it to the bottom first. So first we want to know who's faster. Alright. The problem tells us that we can neglect friction, so that means that the work done by non-conservative forces here is 0, so we're going to be using the conservation of mechanical energy. And if we set for both slides, this point is E1, and for both slides, this is E2, then we know that if they both start from rest, E1 at the top is going to be 0 plus mgh. And we know that at E2, since the height is equal to 0, E2 is going to be equal to 0 plus 1/2 mv squared for V2. So that means that for both Paul and Kathleen, if E1 equals E2, because we're experiencing conservation of mechanical energy, then mgh1, which is the same for both of them. Paul and Kathleen don't necessarily have the same mass, but we'll find out if that matters in a second. mv2 squared. Oh, guess what? It doesn't. And that means that for both Paul and Kathleen, the velocity that they have at the beginning is going to be dependent on the initial height. And if the initial height is the same for both of them, then that means that the final velocity will be the same for both of them at the end. So they have the both same V2 at the bottom. And we were able to show this definitively using conservation of mechanical energy. Now the other question is, which rider makes it to the bottom faster first if we ignore friction? And now here's where you're going to have to think about things a little harder, because you might be thinking, well, if they both have the same velocity at the end, then they both must reach the slide at the bottom at the exact same rate. But just because their velocities are the same at the end doesn't mean that the way they accelerated was the same. Take, for instance, this position shown here. Paul at this point after the start, and Kathleen at this point at the start. If we call this point E prime, just because I'm out of names, we could consider the amount of potential and kinetic energy for both Paul and Kathleen. Paul has barely dropped any height. So Paul, most of his energy at this point is potential energy, and only a small amount of his energy at this point in time is kinetic, which means that his velocity at this point is very small. Whereas Kathleen, at that exact same point, has dropped down a considerable amount more. So more of her total energy is made of kinetic energy, which means that right here, Kathleen's velocity is actually faster. And if we study the shape of the 2 slides, we notice that the entire time that both Paul and Kathleen are falling down the slides, that Kathleen is lower than Paul, which means that the entire time that they're going down the slides, Kathleen's energy is made of more kinetic energy. So that means that she has more velocity, or a higher velocity, throughout the entire experience. So even though their velocities match at the end, since Kathleen's velocity or rate of change of displacement over time is higher than Paul's the entire time, she will actually reach the bottom of the slide first, but with the same velocity as Paul, who gets there later, but accelerated much more at the end. So you might have a question, and you might say, okay, well, energy and work are related, and since work is equal to force times displacement, and since energy is made of kinetic and potential energy, and since we know the work kinetic energy theorem, or we know that work equals change in kinetic energy, and we know that the work to work against a conservative force is equal to the change in potential energy, and the work done by that conservative force is negative change in potential energy, and work will always equal force times displacement. So we could plug in force times displacement for any one of these works as long as we were using the net force experienced. Then you might be wondering, well, why can't I just solve using dynamics? Why can't I draw a free body diagram? And why can't I find my net forces and set them equal to mass times acceleration and then solve? And the truth is that you can if you want to. There's nothing wrong with it. Or you might be wondering, well, why wouldn't I just use energy for everything under the sun from now on? Well, here it is. When do you use energy and when do you use dynamics? If the forces are constant, you can solve the problem any way you like. If you like solving with energy and you have the information, then go ahead, solve for energy. If forces vary or the path is complicated, like a roller coaster or the slides that Paul and Kathleen went down, then you're probably going to want to use conservation of mechanical energy to solve. And it'll be much simpler that way. Because if you had to figure out the overall length of the slide that was curving, or a roller coaster that's winding, you're going to find yourself overall miserable, because that means that the force and the angle are going to constantly be changing in this equation right here, and that would be a pain. Whereas since potential energy only depends on the height above a reference point and the kinetic energy only depends on the velocity and the mass, then holy smokes, that's so much more straightforward. So let's consider a couple of systems that we could say have conservation of energy, and one of them is a pole vaulter. How do we know that the pole vaulter experiences conservation of energy? Well, first thing that we're going to look at is if we're conserving mechanical energy, then we're going to say that we are going to consider this situation and we're going to neglect any effects of friction or air resistance. All right, in the pole vaulter situation, the pole vaulter first has to start with kinetic energy. The pole vaulter runs, and he has kinetic energy. He runs up to the point at which he sticks his pole into, so he's running and he has kinetic energy, and we'll call that E1. Alright, the moment he sticks his pole into the ground, that he begins to decelerate, and that deceleration turns into his energy at E2, which gets stored in now the bent pole, which stores the energy as elastic potential energy. So as he slows down, due to the fact that he dug his pole in the ground, the elastic potential energy within the pole increases. Once that's at its maximum, the pole then launches him upward, so that some of his energy is turned back into kinetic energy as he accelerates upward, and some of his energy is turned into a potential energy. As he accelerates upward, he will actually be slowing down, and so that means that his kinetic energy when the pole snaps forward is going to be converted into gravitational potential energy, which lifts him up. At his highest point, he crosses a bar, and then at his highest point, his potential energy then gets converted back into kinetic energy, which causes him to accelerate back toward the ground. Another example of conservation of mechanical energy would be springs, because you could turn kinetic energy of something speeding up into something into potential energy for a spring. If you run into a spring and compress the spring, right, the spring is going to slow you down, and as you're slowed down, the energy of your motion will get conserved in the form of elastic potential energy. So speaking of springs, let's go ahead and let's take a look. We can use mechanical energy to define the conservation of energies involving spring forces. So mechanical energy is kinetic plus potential. The potential energy resulting from spring is 1/2 kx squared. So that means that when we're considering conservation of potential energy, we could say that the kinetic and spring potential energy at any one point in the system will be equal to the kinetic and spring potential energy at any other point in the system. Just because the force isn't gravity doesn't change the conservation. Spring force is a conservative force, so that means that this equation is also true when the potential energy we're dealing with is spring potential energy. So let's look at this example of a toy dart gun. So we're going to say that this toy dart has a mass of 0.1 kilograms. And we're going to say that the toy gun has a spring in it, and that the spring constant is 250 newtons per meter. If we compress this spring to load the dart 6 centimeters inward, and then shoot the gun or release the spring until it reaches its natural length, or we compress it 6 centimeters, and then we shoot the gun and the spring returns to its relaxed length, then we should be able to figure out what the speed of the dart the moment it's ready to leave the gun is. And we can do that using conservation of mechanical energy for a spring. So here, at this point, the energy, we'll call it E1, and here at this point, we'll call it the energy E2. Now, consider this system. When the dart is loaded, that means that this spring is compressed. It's pushed in, which means that the natural length of the spring is actually 6 centimeters longer than the compressed length of the spring. So that means that here the dart is at rest and the spring is compressed, so 1/2 mv squared plus 1/2 kx squared will equal the energy at point 1. The velocity is 0, so the energy at point 1 is equal to the elastic potential energy, the energy that's being stored due to the spring force. Down here, the spring has relaxed back to its relaxed length, so this is a position of x equals 0, and that's where the spring is here. This position here is a position of x equals 6 centimeters. So at E2, the potential energy due to the spring constant, kx squared, is equal to 0. So that means that all of the energy now is kinetic energy. So we can use conservation of mechanical energy, E1 equals at E2, and we say that E1, 1/2 kx squared, all of the energy is in the form of elastic potential energy, equals 1/2 mv squared for the second position. And I can clean this up a little bit. I can get rid of the 1/2s, and I can say that kx squared equals 1 mv squared. And here the mass does matter. So I could say 250 newtons per meter times, I have to change 6 centimeters into 0.06 meters squared will equal 0.1 kilograms times the velocity squared. And I solve this problem for velocity, and I say that the velocity is going to equal 250 times 0.06 squared divided by 0.100. It's going to be square root. So 250 times 0.06, and that's a squared value, divided by 0.1, and I'm going to take a square root of that, and I get that the velocity that the dart gets released at is 3 meters per second. And that seems like a very reasonable amount. Now, one thing to note is that this example shows the dart being shot in a horizontal direction. So the entire time the change in potential energy due to gravity is equal to 0, which is why we leave it out of the equation. If we were going to include it, it would say plus mgy plus mgy. Here, y1 equals y2. So if you set those two equal to each other, plus mgy plus mgy, oh look, they're the same on both sides, they would end up being removed from the situation, and that's because it's in the horizontal direction only. If this dart were getting shot up or shot down, then the gravitational potential energy would play a much larger role. So let's go ahead and let's take a look at a situation where the gravitational potential energy actually plays a role at the same time as the spring potential energy. So there's two kinds of potential energy in this last example. Here we have a ball, a mass 2.6 kilograms, starting from rest. It falls a vertical distance of 55 centimeters. So that means that the height here equals 55 centimeters. A vertical distance of 55 centimeters. Before it strikes a vertical coiled spring, which is compressed at an amount y equals 15 centimeters. So here the spring gets compressed 15 centimeters. Determine the spring stiffness constant of the spring. Assume the spring has a negligible mass and ignore the air resistance. Measure all distances from the point where the ball first touches the uncompressed spring. So this problem tells us that we set y equals 0 right here. And now we're going to consider this is point 1, this is point 2, and this is point 3. Now let's figure out what is the mechanical energy comprised of in each of these situations. At point 1, the ball is dropped from rest. So the velocity here equals 0. And the height equals 55 centimeters. And the spring is in a relaxed position, so the x of the spring is equal to 0. So the energy at point 1 is going to be equal to mgh. So I can say that that's going to be equal to 2.60 kilograms times 9.8 meters per second squared times a height of 0.55 meters. And that will be my energy for the spring at the first position. And if I solve that, I would want to know how fast is the spring moving here at point 2. At point 2, the spring is made out of potential energy from gravitational plus kinetic energy because it's dropped in some height. But here we've set this as our reference point, so the potential energy at that point is gone. So the energy at point 2 equals 1/2 mv2 squared, or the energy at point 2 is equal to 0.5 times 2.6 times v squared. Now we could set E1 equal to E2 and we could figure out that velocity, and it would actually be pretty straightforward to do so. It's mgh equals 1/2 mv squared. We don't even need the mass. And the velocity here, if h equals 0.55 centimeters and g equals 9.8, then the velocity there is going to be 3.28 meters per second. Now, at point 3, we're actually experiencing something different. At point 3, the energy of the spring is going to be equal to, well, the spring was compressed this much. It's not compressed anymore, so that means that the velocity down at the bottom is going to be equal to 0. Alright, otherwise the spring would still be getting compressed further than 15 centimeters. So that means that here, the total energy of the system is going to be equal to the potential energy due to gravity and the potential energy due to the spring. Now, we can solve for this because in this situation, the energy due to potential is going to be mg, and then it's going to be y, which is actually going to be negative y. And the potential energy due to the spring is going to be 1/2 kx squared. And the neat thing here is that the y of the negative y, that is the amount of height below our 0 point, is going to be equal to the x of the spring. So that means that x equals y, or x equals negative y. And so we can actually solve that, and we find out here that if we solve for the spring constant equals 2 over y squared times, alright, let me write that out a slightly better way. So now we can say that E2 equals E3, so we can say 1/2 mv2 squared equals mg negative y plus 1/2 kx squared, or ky squared. And now I'm going to solve for my k, and I do that by saying 1/2 mv squared minus plus mgy equals 1/2 ky squared. I solve for my y, and my k equals 2y squared times 1/2 mv2 squared plus mgy. I plug in my variables, and I get that k equals 1590 newtons per meter. And so what we did is we just systematically solved for each energy and then used conservation to work our way through. But the truth of the matter is that it actually probably would have been easier to solve this problem if we had set our reference point instead of right here. Imagine if we'd set our reference point here, y equals 0. Well, that would mean that right here, this point would be y equals 15 centimeters. Or sorry, this one would equal, oh no, sorry, now we don't want down there, because we don't know, we don't care. This is the lowest point that we ever experienced. So here we set y3 equal to 0. Here, y2 we set equal to 15 centimeters because it's 15 centimeters above our 0 point. And we know that because that's the compression amount. And then we set this amount here to, instead of 55 centimeters, we set it to 15 plus 55 centimeters, or 70 centimeters. So y1 equals 70 centimeters. Now, why is this easier? Well, now our reference point is the lowest point. We don't have any negative values. Now, E1 is still entirely gravitational potential energy, so it's still mgy1. But now E1 equals mg times 0.7 meters. And E1 equals E3. Well, what is E3 equals? mgy3 plus 1/2 kx squared. It doesn't matter what the speed of the ball was as it hit. All that matters is that the sum of these two has to equal the same thing that mgy1 equal. So now we can plug in. mgy1 equals mgy3 plus 1/2 kx squared. Y3 is 0, so mgy1 has to equal 1/2 kx squared. And we know what x is, we know what y1 is. Let's go ahead and solve for k. K is going to equal mgy1 times 2 over x squared. So that's going to be 2 times 2.6 times 9.8 times 0.7 divided by 0.15 squared. And we do this problem and we say 2 times 2.6 times 9.8 times 0.7 divided by 0.15 squared. And hey, look, 1586 newtons per meter. We got the exact same answer, and our problem was so much simpler just by choosing a better reference point and knowing that energy at point 1 is equal to energy at point 2 is equal to energy at point 3. So we could have solved for the velocity here and it would have been fairly straightforward, but we didn't need to when we broke it down this way into one whole system with one really simple reference point.